Hello, marhaba. Thank you for attending today's talk. My name is Chandra. I'm going to talk about Java's garbage collection today. Just a little bit about me. I'm a Java champion. I'm a JCP Java Community Process Executive Committee representative for my company. I have been programming in Java for a very long time now. I'm a Java User Group leader at two Java User Groups, the New York Java User Group and the Garden State, which is New Jersey Java User Group. I'm an ardent blogger and tweeter. I tweet a lot, in case you have not noticed. I'm a Saganist. I love Carl Sagan. Space is something I'm very interested in. And something that motivates and drives me a lot is coffee. As you can see, I carry a lot of Turkish coffee with me. And I love Turkish coffee. All right, enough about me. I'm going to get started. What are we doing today? Today, we'll talk about Java's garbage. In general, what is garbage collection? What are the different kinds of garbage collection that we have? What are the general patterns of garbage collection? Then we'll take a deeper dive into, some historical generational garbage collections. We'll take a look at the new GC, which is a newer GC. And then we'll also take a look at some very recently added garbage collectors to Java, all with the benefit and intent of understanding how these work and why these are important. We will not go into the nitty-gritty of performance details and tuning yet, but these are important basic concepts that I would like to share first, so we can have an overview of what we are looking at when we go towards a performance tuning in probably a future session. So first, let's start with an overview of the garbage collection itself. What is garbage collection? Garbage collection is a broad definition as 5 things, and we'll talk about that. The top 3 things are looking up some kind of a managed memory area, identifying objects that are still in use and calling them live objects, and marking objects that are no longer live as garbage. Occasionally, we also reclaim some memory by deleting some garbage, and more occasionally, sometimes we just compact memory because objects are placed everywhere in memory. We want to bring them together into one place, so we have more free memory to put new objects into. Where did garbage collection start? It started with a programming language called Lisp. It was created back in 1959, so it's not a new concept we are talking about. The author was John McCarthy, and he's quite famous. He's a founding father in the AI space. In fact, a lot of his contributions is what run AI today. So his contributions are vital. And when he thought about garbage collection, he made some sensible choices doing that. So that's something we would like to keep in mind. What are the different kinds of garbage collection? Now, there are like several different types. So we will only focus on 4 of them. Okay, and pay attention to the 4 that we are talking about, because these are important and they will be inlet into each of the next slides. So based on collection type, how are we collecting the garbage? How are we identifying the garbage as to be collected? Based upon the object marking type, are we marking the objects as live, dead? How do we mark them? And based upon execution volume, so how much of the memory are we actually evaluating for garbage collection? And based upon space compaction, do they compact or do they not compact? Okay, and those are the 4 types we will focus on. These are not the only 4 types. There are several other types, but these are the 4 most important ones we will look at. Based on collection type, and if you notice in my slides, you will notice that I have a little inlet over here that tells you what type I'm currently looking at. This is based on collection type, and the remaining 3 types are grayed out. So you have a visual indicator of where you are. So based on collection type, there are 3 different types. There is a serial type, a parallel type, and a concurrent type of garbage collection. Serial type is basically where you have your application threads that are running, and then they are stopped, and a garbage collection thread runs and determines if memory management needs to be performed of some sort. And while this is performed, application threads are all halted, and application threads resume after the garbage collection thread is done. And this is a stop the world process, in that application threads are stopped while this process is initiated. It's equivalent, and what we're going to do is, for every one of these collection types, we will put an analogy of a mailbox. A mailbox is basically where, let's assume you have a person or a few people sitting somewhere and they're receiving mail, and the mail is being dumped into a slot, and they see all the mail and they have to process this mail. The mail could either be, something like a letter addressed to you, which is important, or it could just be junk, like an advertisement or a flyer of some sort that you're receiving. And we will consider everything that is an advertisement or flyer as garbage, versus mail that is addressed to you and important for you to action as live objects. So that is the analogy we will use. So in case of a serial collection, the real life analogy is basically you stop all the incoming mail that's coming in, and a single person goes in and checks the existing mail to see if it's either relevant or garbage. And that is what a serial collection looks like. So it's a very long drawn process. It is slow and deliberate. The next kind of process is a parallel collection process. Similar to serial collection, application threads are halted, but instead of one, several garbage collection threads can run at the same time. And while they're running, the application is stopped, right? The application threads are stopped. And once the garbage collection threads complete their process, application threads can resume. So this is called a stop the world garbage collection. And this again, based upon collection types. Its real life analogy is you stop all the incoming mail, but instead of one person, there are several people sitting there looking at the mail, sorting it out, determining if it's a relevant mail or if it is garbage, right? So this is a parallel collection. Now there's a lot of confusion between parallel and concurrent. They are different, and here is an example of why. So in concurrent collections, your application threads are not completely stopped. Your application threads may continue to run, albeit at a smaller amount, so a fewer number of threads run. In parallel, garbage collection threads do run alongside the application threads. And once the process completes, all application threads can resume. So this is not a stop the world process as is indicated. So that is something that is different between a parallel and a concurrent collection. A concurrent means you are doing things concurrently, where garbage collection is running alongside application threads. So in a real life analogy, don't stop the incoming mail, let the incoming mail come in, and one or more people are checking the current mails at the same time. So that is an analogy that you can always relate to in terms of parallel versus concurrent. In concurrent, you stop the mail, in parallel, you stop the mail, and in concurrent, you allow the mail to come in. So that is the big difference that I want you to make note of. Now, the second type of classification we'll look at is based on object marking. Is it a precise collection or is it a conservative collection? And let's go deeper into this. A precise collection is like you taking a microscope to every single mail that is coming in to determine if it is addressed to you or it is junk. So you're being very precise. You're looking at everything and deterministically evaluating whether it is a garbage or a live thing that you're looking at. In a real life analogy, you check all the mail and you discard every flyer and junk mail, even if it is addressed to you. You're going over, you're opening that, you're determining that this is not something that's relevant to you, and you're putting it in the trash pile. And that is what a precise collection looks like. Obviously, it is slower than being imprecise, but it aims for thoroughness and not for speed. And that is the most important intent of a precise collection. Useful, but you have to understand that this is slow. It is not as fast as something else we could do. And the something else we could do is what is known as a conservative collection. In a conservative collection, instead of using a microscope, you're using some sort of a lens. What are we doing here? So basically, you are determining if an object is either junk or it is live based upon just looking at if it is addressed to you or not. If it is not addressed to you, it must be junk. And that is basically where you're fastly evaluating whether or not you want something to be determined later as live or dead, right? But it aims for speed and not for thoroughness. So you may still be left with some garbage at the end of the day, but at least you have evaluated some part of it. The real life analogy is basically you check the mail, find anything that is a flyer and discard it. Assume that all addressed mail is not junk. So you've reduced your pile, but it is not as thorough as it would be in case of a precise collection. So conservative is aimed at speed and precise is aimed at thoroughness. That is the difference between a precise and a conservative collection. And these are based on object marking. The third type of classification is basically based on execution volume or run interval, as it is known as, right? So there are two kinds. There's an all at once collection and an incremental collection. Let's take a look at both. An all at once collection is where you scan the entire memory region in order to find out if there is garbage and you discard it. So you're basically not determining a chunk of memory that you want to look at. You take the entire memory footprint and you want to take a look if there is garbage in there or not. So the real life analogy is basically if you have a lot of mail in front of you, you're checking all the mail at once. Okay, and you have to check the entire collection. As you can imagine, this will be slower, but this is sometimes required. The other kind of collection is an incremental collection. In an incremental collection, instead of scanning the entire memory, you scan a section of the memory. You pick up a region, a section, a zone, whatever you want to call it, and you're only processing that particular region. And in this case, since you're only working on slices of memory, it is deemed to be more efficient. So in a real life analogy, instead of checking the entire mail that is in front of you, let us say you pick up one file, you go through it, and then you determine that, okay, I'm ready for more mail to come in or fill this slot. So that is where an incremental collection is different from a complete collection or an all-at-once collection. The fourth category that we will look at, and there's the final category, is space compaction based. So either you are a non-moving collection or a moving collection. A non-moving collection is, let's assume you have your memory filled up with objects, and let's assume for a second that white objects are the dead objects and the black objects are the live objects. So you have some live objects followed by dead objects in this memory graph. And what we do with a non-moving collection is we find all dead objects and so once we remove the dead objects, we're only left with live, but nothing moved. So every object stays where it is, and as long as it's live, it stays in the memory. The real life analogy is you have a dump of mail in front of you, and you basically go select all the flyers and you throw them out, and all the junk mail and you throw them out. But the rest of the mail is still scattered in a pile, and that is what a non-moving collection is. The benefit of this collection is it aims for speed, but not contiguous space. So if new mail comes in, you don't know where to put it, right? But you may have some slots, some packs may be high, some may be low, but you can dump mail, but you have to manage that, right? And that's what a non-moving collection is. On the contrary, a moving collection is where once you have the same memory graph with live and dead objects, not only do you delete all the dead objects, you also move all the live objects to be contiguous, to be together. You pack them. If you have used Windows in the past, I guess 20 years ago, you may know of Windows defragmenter. And this is the same concept that happens in garbage. You're defragmenting your memory by moving objects closer to one another, so you have more free space left at the end of the memory that you could use. Now, this is not thorough and precise. I just want you to know that this is almost an analogy of how it works. So the real life analogy is basically, once you have a chunk of mail in front of you, you not only remove all the junk mail, you also stack the remaining pile into one place, so new mail can start coming in and start filling in the space that you've just cleared up. Okay, and this gives you more room to add more objects without having to worry about where to put the object. But obviously, this aims for contiguous space, and therefore it is a bit slower compared to the non-moving collection. So you have to understand why all of these are important, because in some cases you want to choose one over the other. It will almost certainly feel like you want to do a precise all the time or moving all the time, but those are expensive operations, which is why their counterparts exist. And that is something useful to know. Great. So the next topic we'll move into is, after we're done with all the mail analogies, we're done. We don't want to talk about that anymore, is we'll take a look at some general patterns of how this works. The first thing we'll take a look at is two definitions. What is a root object? That is something you'll hear quite often. And the second is a very interesting concept called the tricolor marking. So let's take a look at both. What is garbage collection? Just a quick recap, right? We talked about the 5 different things that a garbage collection typically defines, which is looking up, identifying objects, marking objects as garbage, occasionally reclaim, and occasionally compact memory. So we'll focus on marking objects that are no longer used as garbage. How does a system do this? And that is something that we'll focus on. So first, let us start by looking at what is a root object. A root object is several things, right? A system class is a root object. A local variable you declare in your program is a root object, could be a root object. A thread could be a root object. And there are many other things that could be a root object. A very comprehensive list that I found useful when I first created this presentation about 4 years ago is at yourkit.com. The link is included below. They do go into some amount of details of what is included. Of course, this presentation is also shared. If you look at your chat, you will find the link to where you can go download this presentation as I'm talking to you. So please feel free to take a look at other root object definitions. But this is an important concept for you to know. Tricolor marking is something very interesting. This is something that is not taught often, but you basically paint objects with colors. Now, this is just a visual representation painting. You don't really go paint anything, but imagine that an object can have 3 colors associated with it. you mark an object as gray to begin its evaluation process, saying, I don't know if this object is live or dead. Then you can have two different states, which is either a black state in which the object is evaluated as being live, or a white state in which the object is being evaluated as garbage. So there are three states. There is a gray state, which is I don't know, and there's a black, which means it is live, and there's a white, which means it is garbage. So remember these three, gray, black, white, gray being unknown, black being alive, and white being dead. Now, switching topics, let's take a look at three patterns. We talked about classifications already. Classifications are how garbage collection can be classified as different types, and patterns is how garbage collection works. So there are three different patterns that we will like to focus on. Once again, this is not a comprehensive list, but this is something meaningful and useful to what we are doing in this session. So the first one is no longer used. I want you to be aware of this, but we're just going to give you an overview of this because this is important and relevant to other garbage collection patterns. So first one we'll take a look at is reference counting patterns. So basically you take an object. These are called root objects. We just talked about root objects. You start from a root object and you see what it references. And basically you start marking counters of those. And once some object is unused, the reference counter decrements, and therefore the object that is associated with it is marked as garbage. And that is where a reference counting algorithm works, but this is not used in Java anymore. It was probably introduced as an experimental feature in the first version of Java and later discarded very quickly. This does not have a lot of meaning and use in a large ecosystem where you have a program that can have multiple objects associated and deeply nested objects nested with it. So the first one we'll take a look at that is very interesting to us is a mark, sweep, and optionally compacting algorithm. And that is super cool. So the objects to be evaluated are first all marked in gray. And let's assume they are compacted together for now, as an assumption. So there are 6 objects we have, and then there is free space left. And this is at the beginning of the GC cycle. What we do is we mark all the objects as gray, gray being I don't know if it is live or dead. Then the next stage, we actually evaluate the objects as being live or dead. We take a look at the reference counts, we look at the age. There are a few indicators, we'll go through them. Don't worry, I will go through all of those details later. But we are marking. So this is the mark part of the mark, sweep, and occasionally compact algorithm, where I'm marking the object as either live, black, or dead with a white. So my objects are marked as live or dead. So right now we notice that O2 and O4 are both dead objects. So the dead objects are swept off, and that is called the sweep. So mark, then sweep. So we are sweeping off the dead objects. So we're left with O1, O3, O5, and O6 being the objects that are alive, and the dead objects have been swept off. Now, this process in itself should complete the mark sweep algorithm. So you don't need to do anything further. But as you can notice, your memory is now fragmented. This is great and it works, but sometimes you reach a point where you have a large object and you cannot place it in the memory because there is no free contiguous space left. And at that time, you have to run what is known as a compaction. And this is an optional step. And when you do a compaction, you move all the objects right next to one another. So you have contiguous free space. And that is called a compact stage. Now, so you can either have a mark sweep or a mark sweep compacting pattern. So there are 2 different patterns and you have to be aware that both are possible. Obviously, the compacting is slower because there's a lot of different things that have to happen. Objects have to be moved and the references to the objects have to be repointed to their new memory locations. So it's more involved and it takes up more time. So you don't want to do it often. And this is what is usually the slowest part of garbage collection. The second pattern that is very relevant to us is actually an improvement on the first one. This is called a copying collector. And in a copying collector, what we do is the space is divided into 2 equal areas, and your objects are only allocated in one of the 2 areas. This area where it's allocated is called a from region. And there is a to region that is empty all the time. Okay, and this is where objects are being evaluated. Let's take a quick look at how this evaluation happens. So the GC cycle begins very similar to the mark sweep algorithm. You mark all the objects as gray because you don't know if they're live or dead. And then you perform the same evaluation of objects being marked as live or dead. Same example, O2 and O4 are marked as dead. So O1, O3, O5, and O6 are then moved into another region, and this region now becomes the from region, and the region from which they were moved becomes the to region. And what we then do is we purge everything from that region. So basically, we are moving objects to a new region all the time and switching between the from and tos. So every time the region becomes the holder of the objects, it is marked as a from region. So a from region will switch to a to region, and a to region will switch to a from region. Now, always remember, this requires having space divided into two equal areas. You cannot have unequal areas because you have to have the expectation met of the same number of objects being able to be pushed around. And objects are physically moved, so everything in the old region can be removed. And that is something very useful, in that you don't have to no longer worry about which objects to compact, how much time it takes. You're blindly taking all the objects that are live and putting them together in a new region. And so they are automatically compacted. You don't have to run a separate compaction algorithm for this. Now, this works in some cases, and the mark sweep works in other cases. So these are two patterns that are quite relevant. Now, where are they useful? So mark sweep compact, mark sweep and occasional compact, of course, is efficient for larger memory areas, where copying is efficient for smaller ones. Mark sweep works for longer lived objects. So if an object has a very long sustained life, mark sweep is better. Copying works for short lived objects. So if an object is supposed to be only existing for, let us say, the scope of one method, you probably want to put it into a smaller space and have it copied over as long as it is alive, and remove it once it's dead. A mark sweep can either be incremental or an all at once, because you can determine the size of memory that you're working in, and you can do mark sweep on that. However, a copying has to be all at once, because you cannot copy part of the memory. You have to work on the entire memory and move it along to the next one. Mark sweep does not require any extra free space, whereas copying requires 2 times the memory space of the current space that you're working on. Mark sweep can either be concurrent, because you can create a concurrent mark sweep. Obviously, that's not compacting. So concurrent means your application threads continue to work, in which case you cannot move objects because the application threads depend on these objects. So you can create a concurrent mark sweep algorithm where objects still remain where they are and fragmented. Or you can also do a stop the world, in which case you are also compacting. So there are both possibilities for mark sweep algorithm. However, with copying, you cannot have any concurrency. You have to physically do a stop the world, and therefore no application threads can run while you're copying things over. Now, your question will be, why would I even do this? It is very efficient to do copying algorithms on a smaller footprint, and we'll show you why. So the next one we'll take a look at is a deeper dive into generational garbage collection patterns. So the generational garbage collection patterns are quite important, and that's where you'll see the relevance of using both. So starting with Java 5, garbage collector started segregating itself into generational patterns. What is a generational pattern? It divides the memory into smaller areas, 2 different areas, and collection patterns are different per area. So there is one area that may have one collection pattern, mark sweep or copying, and another area that may have another collection pattern. Now, this is based upon what is called the weak generational hypothesis, and this is not something I made up. This is a standard hypothesis. Most objects don't have a long life. So most objects that you create don't live for a long period of time. They're usually scoped locally, or they die quickly, or they nullified quickly. And typically, and most often, older generation objects do not depend upon younger generation objects. So an object created in the past should not typically depend on an object that is created later. You will question why it is even possible, but there are instances where that is possible, and we'll if time permits, we'll take a look at that. Now, here is how a generational garbage collector looks like. You have a young generation, you have an old generation, and then you have a permanent generation. So we're going to ignore the permanent generation. This is where your class definitions, your static variables, etc., are defined, and you do not do any. Typically, you don't do any garbage collection in the permanent generation area. Now, there may be other non-JVM, non-standard JVM, I shouldn't say standard. There may be vendors of JVM who may choose to do garbage collection on the permanent generation. The spec does not require it. That's what I mean. Okay, so you have a young generation which is comprised of 3 regions, and we'll talk about this, and an old generation that is comprised of 1 region called the tenure. We'll take a look at all of these, so don't worry if you don't understand these terms or you already are aware of them. Bear with me for a second. So when you start your memory, you have something called an initial size of your memory, and this is the initial size that your memory will occupy. And then you can always expand to a reserved space, and this is called the maximum size. So these are parameters you probably have set when you were working with Java, in that you probably wrote an XMS or an XMX, XSS, etc. These are basically initial sizes and maximum sizes of memory. You never want to start with your full memory. The larger the memory that you use, the more time it takes to garbage collect. So if you have an application that is running slow, please do not add more memory to it, because that may further slow it down. Maybe your application is currently crashing because of the amount of memory it has to go through to find objects or space. And that could be one of the reasons your application could be slow. So more memory does not mean fast. More memory could actually mean slow. So that is something I want you to keep in mind. So when a garbage collection runs on the young generation, it's called a minor garbage collection. This is supposed to be fast. So that's called a minor GC. And you want as much of minor GC as you can use, rather than do what is known as a major GC, which works on the tenured region or the old region. If you don't understand this term, bear with another 2 slides and you will. So here is how a garbage collection works from Java 5 and not currently. So this is an older version of the garbage collection, but it's an important basic to know. So when an object is created, it is put into what is called Eden. It's a biblical reference. Eden is basically where new objects are created and stored. So anytime an object is first created, it is put into what is called an Eden space, and it is given an age of 0. So please notice on the side that I'm also, as I'm going through the slides, the side notes will increase. So when you first create an object, you put it into an Eden space, and you basically, after the first garbage collection, if the object is still alive, you move it into a survivor region. So it is a copying or a moving collector. I am actually moving objects from Eden to survivor. And when I move an object, I mark its age as 1. And in this case, the survivor 1 becomes what is called the to region of where I am moving an object to. Okay, so the next garbage collection cycle, I take whatever is available in Eden and whatever is in the current from region, that is the survivor region, and I move all the live objects from there into survivor 2. So this is the from region at this point, and survivor 2 becomes the to region. So I'm moving all the objects from survivor 1 to survivor 2. Obviously, this is a copying pattern, and survivor 1 and survivor 2 should have the same size. Eden can have a different size compared to survivor 1 and survivor 2. So Eden is just an entry point. However, survivor 1 and survivor 2 are the copying pattern algorithm that we talked about earlier. Now in the third garbage collection, and I forgot to mention, while I do that, I also increment the age of the live objects by 1. So objects from Eden to survivor will get an age of 1, and objects from survivor 1 to survivor 2 will get an age of 2, because obviously Eden is where the age is 0. The third garbage collection cycle is similar in that I take objects from Eden that are newly added and objects from survivor 2 that either were added from Eden in the past cycle, and I basically evaluate them for being live, and if they are live, I move all such objects into survivor 1. So the pattern simply keeps repeating itself, survivor 1 to survivor 2, and anything from Eden that is live. So age is always incremented, and this goes on for a period of a certain time, and by default in Java that certain time is an age of 15. 15 is when an object is considered old enough to be moved into a tenured region. I'm sorry, I think I moved too quickly. Bear with me. And once this is done, at the nth GC, which is probably the 15th GC that we have, when the age is around 15, we move the objects into the tenured region. And this is when an object is considered an old object. And this is when an object, if it has to be garbage collected, will have to undergo what is known as a major garbage collection. So once again, this is just a text of whatever I just talked about. I'm going to skip this. The one thing I would like to say is method definitions and statics, etc., are allocated to PermGen that need not be collected. I'm very careful with the use of the word need not, because the JVM specification does not require you to perform garbage collection on the PermGen. But there are some instances of the JVM that can. Okay, so now we notice that there are two different patterns. There is a young generation and an old generation, and it is possible to have different garbage collectors for each. So for the young generation, that is the Eden and the survivors, you can either have a serial garbage collector, you can have a parallel garbage collector, it's called parallel scavenge, and there is a concurrent mark sweep garbage collector where you can use a parallel new. So the GC type is either called serial, parallel, or concurrent mark sweep, which implies that for the young generation, I do serial, and for the old generation, I do serial. It's a stop the world in both cases. A parallel collection would mean I do a parallel scavenge for the young generation, and I do a parallel for the old generation. A concurrent mark sweep indicates that I do a parallel collection for the young generation. It's almost the same as parallel scavenge. So they're both almost the same. It's just a difference in the implementation. But for the old generation, instead of doing a parallel, which is a stop the world, I do a concurrent mark sweep algorithm. Okay, and the concurrent mark sweep works until I reach a point where I can no longer just delete old objects and leave objects strewn around. Then I actually have to compact them, and that's when a parallel process kicks in to actually compact. So a concurrent mark sweep is not completely, I guess, stop the world free. There is a stop the world process that you eventually reach when memory becomes fragmented enough that you cannot allocate new objects because there's no contiguous space to do so. So always imagine, let's assume I have blocks and I want to introduce a block that is this big into a space that is only allowing me half the size of it. So that's the problem when I have to actually move all the current blocks together to create enough space to put this block in. And that's what happens in a concurrent mark sweep at a certain point of time. So understand that concurrent mark sweep will always not be concurrent. Okay. The next thing we'll talk about is the newer garbage collections, right? What started with Java 8. So the first, why do we need a new garbage collector at all? The old garbage collectors focused on live objects and not on garbage. And this is a problem because a lot of live objects exist and a lot of time is spent evaluating if the object is live or dead. Contiguous memory area management requires a lot of flexibility, and that's not easy. It comes at a cost, and we'll take a look at that. Different collectors for different regions means you have to create combinations, different kinds of tweaking. You want to avoid that. You want to have the same GC process across. Also, there is an unpredictability associated with garbage collection because you cannot predict the pause times. Or pause times is the amount of time the application is halted or paused for the stop the world collection to happen. So it's unpredictable. Sometimes it could be milliseconds, sometimes it could go up to seconds, and your application may simply not perform at times when you were expecting it to. Also, it requires heavy tune-ups to pause and stabilize the pause times. So you basically have to tune it with all kinds of different settings that you can create. In fact, there were about 70 known tune-ups possible for most GCs in the past. It is not performant for large memory heaps, obviously, because what do? You create a small area for your young generation, but you have a vast region for your, let us say, tenured region, and garbage collection becomes a challenge. And if you use, let us say, if you come up and say, hey, I'm going to just use concurrent mark sweep, you're highly prone to fragmentation. And therefore, what happens is there is a demand to create a smaller heap to make it more predictable, because the larger the heap and the more fragmented your objects are, it takes longer to garbage collect. So that there were some very solid reasons why the past generational garbage collector no longer works efficiently. So here comes the new model, and this is a very quick preview of how G1GC looks like. G1GC stands for Garbage First Garbage Collector. In the Garbage First Garbage Collector, the first thing you'll notice is the memory is not divided in a sequential manner, but it is more scattered, right? This is the intent. Now, in reality, it may look different. In reality, they may be more contiguous than it looks like, but that is something beside the point. I just want you to understand how G1GC actually is intended to work. So you have your Eden regions, you have your survivor regions, and this could be a survivor S1, this could be a survivor S2, we don't care. And then you have your tenured regions, which is where older objects reside. And we have a new region called humongous region, and we'll talk about this. And then the rest of the blue is basically your free space. So free space allows you to grow things further. And you can mark regions. Every single square, the small square that you see, is a region. And you can mark a region as Eden, survivor, tenured, or humongous. And we allow the JVM and memory management to take care of that. We don't have to do it ourselves. So that is something that is the basis of the new G1GC. Let's delve into some details. So what does an Eden region look like? The Eden region itself is divided into smaller memory areas. It's a block of memory, and therefore you can put objects anywhere within that block of memory. So everything that you see in green here is basically part of an object. So this object occupies 4 blocks within this region, and then this object occupies 1 block within this region. These are just indicators of how much memory is being used. Whatever you see in the light gray, pale gray, is basically unused part of this region. So a region does not have to be filled up. A region can have some objects in it. That's what I'm trying to communicate with this inlaid picture. Now, regions themselves have some logic associated with them. So let's go through that. A region is a contiguous unit of memory. So one region is 1 block of memory. It is not spread over a lot of areas of memory. So you have a region in a specific space. It is the basic block for both allocation and for space reclamation. When you reclaim space, you're reclaiming a region. You're not reclaiming parts of a region. When you allocate to a region. You do not allocate to more than one region. Regions are formed by basically dividing your memory into 2048, or more. They have to be at least 2048 regions. They have to be equal in size, and that is how you break your memory into smaller portions that you manage. And we'll take a look at the math in a minute, but I just wanted to let you know how this works. The region size can be anywhere from 1 MB to 32 MB. So beyond 32 MB, it doesn't make sense to do this. And this is still an older garbage collection, if I may. G1GC is not modern. It is Java 8, and we'll see why. The memory manager assigns the region, you don't. But in spite of all that, you can, the regions are divided into free, Eden, survivor, and tenured, but you can override these, right? You can create your own regions, and I'll tell you how to do that in a minute. When you create a large object, it gets its own region, and it's called a humongous object. And I'll go into the math in a bit. I just want you to know that this exists. So the way I'm going to do the math is, I have a lot of appendices. I don't have a lot of time to go through the appendices, so I'll just let you know. I'll do one right now, but going forward, you have this access to this presentation. Feel free to take a look at it. There are appendices at the bottom. Please feel free to navigate to that. So let's go look at the region math real quick. If you have a 9 GB heap, this is how the math works. And this is basically how the JVM is calculating your regions for you. So it takes your 9 GB and converts it into MB. So it's basically a multiplication with 1024 MB, which is 1 GB each. So it creates a megabytes equivalent of your heap. Then it basically has to calculate the number of regions, which we determined to be 2048 or more. So it divides the current memory by 2048, and therefore it gets 4.5 MB per region as its logical choice. Now we did say it is a power of 2. So it calculates the power of 2, that is it is less than 4.5, that is, let's say 2 square is less than 4.5, and then calculates the power of 2 that is greater than 4.5, that is 2 to the power of 3. So you can get a 4 MB region, which means there are 2304 regions, or you can create an 8 MB region, that means there are 1152 regions. But we already declared that the number of regions should be 2048 or more, so logically it will pick the 4 MB regions and create regions of size of 4 MB. When it does this, it also knows and is intelligent enough to figure out that any object that is greater than 50% of the region is called a humongous object. So any object that is greater than 2 MB will become a humongous object and get its own region. Now, since it did this math for you, you basically have let it create regions and determine what is large objects. And these large objects matter because anytime you try to move a large object, you have to do a lot of space calculation and you have to change pointers. And this is not an easy move because let's assume an object is occupying several regions. Moving that object is something that you don't want to do often. So it has its own garbage collection process that we'll take a look at. But again, I'm going to avoid going into appendices in the interest of time alone, but the appendices exist for every single one of the next slides. So please be aware of that. Here is how the G1GC cycle looks like. Okay, and the first thing I want you to understand is there is a single garbage collection pattern going on. There is no two patterns, right? In the past, we had a minor GC and a major GC of two different regions. this does not follow the same logic. You have two different phases. You have a young only phase, that is the top half of the semicircle, and that's where you want to be all the time. And then you have what is called the space reclamation phase, where you don't want to be all the time. Okay, and we'll take a look at that real quick. So the way the garbage collection works is it begins here. Let's go to the next slide so it is easier for you to understand. I wanted to take a quick digestion of this. There are 5 steps. You have what is called a young collection, and then after a certain point, it reaches what's called an initial mark. And while the initial mark is going on, you do concurrent marking. And once the concurrent marking finishes, you go through what is called a remark cycle. And once the remark completes, you go through cleanup. And once the cleanup determines what to do, you either go back to the young collection, so you go through the dotted line and back to the young collection and repeat this cycle, or if the cleanup determines, hey, you have had so much fragmented memory that you cannot move forward with your current young process alone, is when it goes into a space reclamation phase where objects are moved and compacted. Okay, and this is the second cycle that you would like to avoid. This is an equivalent of the major GC that you remember. Okay, so the next slide goes into a little bit more detail. It starts with the young collection, which runs periodically. And there are certain garbage collection thresholds that determine whether or not young collection should move forward. So young collection keeps happening. So every few intervals, there is a young collection. And each of these circles that you see here is a stop the world. So you notice that there is not a massive stop the world anywhere. There are just a few stop the worlds that are happening in between. So in general, even if you don't do anything to your program, if you were to move from, let us say, a Java 7 to a Java 8, recompile and run your code on Java 8, your program will be faster just because of this cycle. The garbage collection has improved, right? And that is something very useful to know. You go through what is called an initial mark. This basically looks for all the root objects and triggers what is called the concurrent marking. And it continues the young collection. So young collections, the small blue circles continue at the end of this, right? So initial mark is an important starter phase. It doesn't do anything else. Concurrent marking is awesome. This is one slide which I'm going to probably quickly jump into in the appendix to show you how this works. So going through very quickly, this is your Eden plus Survivor. The same picture we saw for generational garbage collection, where I have the Eden region. I don't know what happened to my marker. Okay, you have the Eden region and a Survivor region, and all live objects from there are moved to a new Survivor region. So basically what we do is we take an empty cell and we move all the live objects from Eden and Survivor 1 to the Survivor 2. So Eden and Survivor from to a Survivor 2. Either way you call it, right? And this is part of the young only collection process. And that is what is happening. The other part of the young only process that you notice is you can have objects from, let us say, Survivor, and these objects are basically aged above 15, and therefore they go into a new region called a tenured region. And you'll notice that I create a tenured region at the end of this process. So there is both the minor GC equivalents of moving objects from Eden and Survivor 1 to Survivor 2, and the moving of objects from a Survivor age 15 to a tenured region happening within the cycle in the young only phase. The initial mark is basically where I have marking objects as live or dead. So I'm determining if the objects based upon their root scanning. Gray is basically I don't know if they're live. Black is basically where I know that they are live, and white is basically I know that they are dead. And that is what an initial mark does. I know that they are dead because there are no references to this object that I know of, is what I'm saying. Okay, it may be that there are references to the object elsewhere that I don't know of, and I'll take a look at that in a minute. So bear with me. So I have just done an initial mark based upon what I know. So this is an imprecise marking mechanism at this point. I just don't have references that I know of. Okay, and then what is the most cool aspect is the concurrent marking. So here is how concurrent marking looks like. Think of it like you taking a photograph. This is a photograph of your memory. It takes a snapshot. And what it does next is basically does a process called snapshot at the beginning. So that's a photograph. It took a picture of your memory. Okay, it has the object graph of every single object that you have. Now, any change made after the snapshot at the beginning is ignored. So if an object is introduced after the snapshot has been taken, it is considered live. So it's a conservative collection. So yeah, I don't know if you recollect, but we talked about conservative, where if I don't know something, I'm going to assume it is live. So any object added after the collection is after the snapshot is taken is marked as live, and then a root scanning process is initiated. So all root objects are marked in gray. I don't know if you can see that there is a little gray dot on each of the root objects, and they are evaluated for being live or dead. The new objects are still ignored. Same way, if an object is dereferenced after the snapshot is taken, that object is still considered live, because when I took the snapshot, that object was live. I don't really care what happened to the object afterwards, because I'm a conservative collection. So root objects are then marked as live or dead. So you notice that I have a root painting going on here. Live roots are marked as black, and the dead root is marked as white. Okay, and then the next chain is evaluated. The children are painted as live or dead based on that. But all objects that were added after the snapshot was taken are considered live. Any object dereferenced after the object was collected is still considered live. That is something important to know. That is the only difference, but basically it's a conservative collection. But what it does is gives you the ability to scan and determine if the objects are live or dead. Now we go through what is called a remark phase. Okay, and this is where, I don't know if you recollect, but in the initial mark, I marked an object as dead because there was no known reference to it in my region. Now I go through what is called the remembered set, and I look for any objects that may be referencing my current marked dead object because it had references in some other region. And I find such objects, and if I find such an object, I mark it as a live object again. Something going wrong with my marker, so I'm going to stop using it. I'm going to use my mouse, so bear with me, please. So I mark those objects as live again. So an object that was marked as dead has been remarked as live because a reference to it was found elsewhere. And once a reference was found elsewhere, I put it into what is known as a remembered set. So the next time I do garbage collection, I can look up this remembered set to determine if this object should be marked as live or dead. And that's super cool. So that is what is happening. So the next thing I want to take a look at is the cleanup process, where what I do is I get rid of all the dead objects that are remaining. So any dead object in the region is removed, but the memory is not still compacted. So it's still a cleanup phase. What also happens in the cleanup phase is I determine how much of the usage of the memory is going on. And if there is a lot of use of memory and I don't have contiguous free space, and this is not just across one region, it's across a collection set. So it's an incremental collector. I don't know if you remember the classification, but instead of looking at the entire memory, I look at chunks of memory. And if I find that within my collection set, there is little space left, or a threshold has been reached where I have to compact, the space reclamation or the bottom part is reached. Okay, and very quickly looking at the bottom part, I'm actually going to not do that right now, but the space reclamation phase is basically where you pick up some regions from the minor GCs or the younger generations, and some regions from the tenured regions, put them together and do a garbage collection compaction process on it. The intent being that the pause time is consistent. So you aim for constant pause time, and therefore you collect some regions of tenured and some regions of, let us say, a young generation, and group them together and perform the GC process on it, with the expectation that you will complete that process in a given time. So it's time-based, pause time-based, and that is how the GC works in case of a space reclamation. So obviously, you cannot reclaim all the space at one go, and therefore you have several space reclamation spots that happen until the GC process evaluates that it is no longer required. And that is something useful to know. Okay, stepping back, that was everything that we just talked about, and the same thing in text is it updates the internal structures, reclaims, determines if a space reclamation is needed, and triggers a young collection if it is not. So it either goes from the cleanup to a young collection back to the top half of the hemisphere, or it determines that a space reclamation is required, which is when it enters the painful and slow second part of the hemisphere. So that is how G1GC in general works. Once laid out and once you sort of grasp this, it's actually a super simple concept. It's not much, but there is a lot going on, and there's a lot of, I guess, technicality associated with which I'm skipping right now, which it makes for an interesting read if you're interested in that kind of stuff. So if you are interested, I'm happy to discuss that at after this session. Now, there was something called permanent generation. We talked about this when we talked about generational GCs. PermGen was allocated as a part of the JVM heap. PermGen is implicitly bounded. So when you start your JVM, you get a certain amount of PermGen, and that is what you have to deal with. And if you have written any major Java program, you would have probably encountered an out-of-memory error, out of PermGen space. That is basically it, in that you have exhausted the amount of PermGen space you have. Either you created a lot of static objects, or you created a lot of methods, etc. Whatever you've done, and that is when you get those errors. Now, PermGen was implicitly bound because it was given to the JVM on JVM startup, and it is constant. You cannot change it once it's created. And it could not avail of the underlying operating system memory swap. So you could not actually use a swap file to put it onto file and bring it back. PermGen was in memory, and therefore you do run out of memory. And what is worse is that the PermGen was 64 megs in size, and of course it was 85 megs for 64-bit scale pointers, but in general, if you're writing a Java application, it was just 64 megs. And that sometimes with certain incorrect approaches, that is very easily reached. So that is now replaced with what is now called Metaspace. Metaspace is a different concept, but it does not stop your out-of-memory errors. So don't assume that it is magic and it will immediately stop you from getting out-of-memory errors. No. The only difference is, instead of the JVM being given some amount of memory to use as PermGen at the startup, Metaspace depends upon the underlying operating system. Okay, so it's very similar to any other program running on your application. Instead of being bounded, it just relies on the underlying operating system to provide a swap space to do whatever management. It has an initial metaspace very similar to initial perm size, and there's a max. And if you don't set a max, it is set to infinity, whatever is available on your machine. So if your machine has a lot of RAM on it, it will all get used. And that is basically what the benefit of using a metaspace is. Now, this also leads to bad programming, so you should be aware of that. So avoid, setting the metaspace to infinity. Do set it to a value. The last section that I wanted to cover today was recently added garbage collectors, and this is an awesome addition on every single thing that we've built up so far. Right. The first one I'd like to talk about is Z garbage collector, which was introduced in JDK 11. Z is efficient for very large memory heaps. One of the best aspects of Z is its predictable throughput. Throughput is the opposite of pause time. So the amount of time an application spends processing its own needs rather than wasting time on garbage collection is called the throughput. ZGC has low GC pause times, and they never exceed 10 milliseconds, and that's what ZGC works with. Now, ZGC works on a specific region. They create what is called, instead of regions, they create what is called Z sets. In some countries, Z is Z, but it is almost the same thing I'm saying. So Z sets or Z sets are created. And one of the guarantees it gives you is no more than 15% application throughput reduction compared to using any other GCs. It aims at simplifying the tuning. So there are exactly 5 different tuning options that you get compared to the 70 we had in the awesome for memory pressure testing. So what happens when an application reaches the memory thresholds? How does it behave? Is something you can test with Epsilon GC. So when you turn on Epsilon GC, you're telling JVM that I have a GC, but it does nothing, right? And the easiness with which new garbage collectors are coming out is because there's now something called the GCI, or garbage collection interface. So there's now an interface in the JVM that allows you to create your own garbage collectors and hook them into the JVM. Okay, and that is what allows for creation of many new GCs that we will look at, and it's an awesome addition to Java. However, Epsilon GC is something I would like you to take a look at, especially when you have, let us say, a batch job that you really don't care about GC, and you have thrown enough memory at it that you know that your application won't actually suffer, and now you can get performance on without any kind of GC latencies on that particular batch job. So there is a benefit to Epsilon even in real world production scenarios. The third GC that I'm going to talk about is Shenandoah. And Shenandoah is the most recent joiner of the GCs. It is a non-generational garbage collector. It is based upon some very cool concepts which are quite similar to what ZGC does. I did not explain this in the ZGC, but the way this works is when an object is loaded into memory, it is given what is called a load barrier. And that load barrier is basically a threshold to when that object is actually loaded after you've requested it to be loaded. Because of this load reference barrier, anytime someone asks for the object, this load reference barrier is reached and it determines where the object is located. So if the object is moved to some other location, this load reference barrier is updated, and therefore you don't have to go change any reference pointers elsewhere in a lookup table. When an application or some other thread requests for this object, the same load barrier is reached and it knows to point to the new location. And that is what something Shenandoah GC does very well. Its pause times are supposed to be independent of the heap size. So you bring it something like 2 GB or terabytes, it'll have the same consistent pause times. It's great for responsiveness and predictable pauses, and there's some reading material included. There is a lot of material on Shenandoah, in fact, a lot more than even ZGC has. Red Hat has spent a lot of time documenting this and explaining how it works. So there is generally a question about which one should I use? And I cannot answer that question in all honesty. There are different, I guess, tests done by different companies, and I've included a few that I found useful. The links are here. Make your evaluation based on your needs. It is not that one is better than the other. I actually believe that I've used both Shenandoah and ZGC, for example, and I see value in both. But of course, you should make your evaluation based upon your needs. Now, I guess with that, I am done with my slides. I'm going to take a look at the questions that came up. And the questions are, I see two questions here. How do you avoid stopping the world in real-time applications to avoid lags in availability? So, great question. The answer is you can't. Sometimes you cannot stop stopping the world. It depends on how efficiently you write your program. Maybe you don't create a lot of objects. Maybe you manage your objects to be young generation only, and there is still a stop the world there. It is not going to impact you, but you will always have a stop the world. You can reduce it, but you can never eliminate it. And the reduction is basically ensuring that you don't declare anything at a class level, or you try to minimize the scope of an object. You nullify references as often as you can. Don't nest objects. Don't just plain old memory management. The second question I see is, what tools are used to monitor GC? Several tools. My favorite is basically Visual VM. I start there. Visual VM gives you an amazing indicator of how your memory graph looks like. It gives you details about what garbage collection cycles are running. There are several vendor tools out there as well. Those are commercial, so use per the license agreements you have at your workplaces, or if they have a trial version, understand what the limitations are. But yeah, start with Visual VM. I mean, the first thing you want to do is understand the memory graph, understand the heap, understand where objects are being allocated and where your memory is being used up. That is where I guess you want to start with the process of the tooling that you use to monitor. Another thing that I would say to add to that is JVM is your best friend. The JVM provides for amazing unified logging. And starting Java 8, the logging process has been unified into one single way of logging. So you don't have a GC logger separate from, let us say, some other loggers, that is a thread logger or a thread dump logger, etc. Everything follows the same logging pattern. It's very similar to what you use in logging for your application, and there are some customizable components to it. My appendix does include them, but I'm going to skip that for now. But yeah, if you do look at my slides, you will see an appendix where the logging information is also stored. Another question that came up is, what extra considerations should be taken when running inside containers? Great question. So number one, try to move to a more modern version of Java. And this is because older versions of Java, especially until, let us say, Java 10, ignored the memory settings that you put on the container. So even if you were on a container and you specified your memory usage as cut off to 2 gigs, for example, it could take up to 4 gigs or 5 gigs, and there's nothing preventing it. It goes to the host, reaches out and gets more memory and uses it. So it can steal memory from other, I guess, other processes running on that host. So what you want to do, number one, is move to a more modern version of Java. If not Java 11, which is the LTS that your workplace may recommend, move to even a more modern version. The more modern it is, the better it is for you. So Java 11 has the benefit of now including Shenandoah in it. So if you get a more recent release of Java 11, you also get the benefits of using Shenandoah there. So that might answer your question. I don't know if I did, but yeah, that's the only constraint that I have used when I'm using containers. I don't know if I answered all the questions. Please do let me know if you need any more details on whatever I said.
Well, thank you, Chandra. Actually, all questions are answered. Thank you for your waving. And we will finish this presentation and continue to our workshop soon. Thank you for your presentation again. Bye-bye.
Bye-bye.
Thank you.